All right, next example. When the source of a frequency vibrates at 512 hertz, a stretched string resonates at the 7th harmonic. What is the next resonant frequency? All right, so the first thing we can do here is if we remember the rule that says, well, f of n must be equal to nfo. So let's solve for the fundamental or the first harmonic. And if we do that, we can then solve for any other possible one. So what we're going to do is say, well, if the frequency of the 7th is equal to 7 times the fundamental, then therefore the fundamental must be equal to frequency of the 7th divided by 7. So in other words, 512 hertz divided by 7. So all we're doing is rearranging. So if I do that, I get 512 divided by 7, and we see that the fundamental must be 73.1 hertz. Well, the next resonant would then be the 8th harmonic. So therefore, if I want to solve for the 8th harmonic, we say, well, frequency of the 8th must be then equal to 8 times the fundamental, which in this case was at 73.1. So if I go 8 times 73.1 hertz, I end up getting the fundamental or the frequency for the 8th to be 585 hertz. All right, let's try the last question. A 70 centimeter stretched string has a fundamental frequency of 262 hertz. If the string is cut to 50 centimeters, but the tension remains the same, determine the new fundamental frequency. All right, so let's kind of look at what's happening here. So what we're saying is that here we have a fundamental frequency, which is exactly equal to half a wave. And the distance from here to here, we said was 70 centimeters. And the fundamental frequency for this section, I'm just going to say FO, for the first one is 262 hertz. If the string is cut to 50 centimeters, but the tension remains the same, determine the fundamental frequency. All right, so if it's the same string, the same tension, just a different length, we can assume one thing. We can assume that the speed remains the same. So really, if I can solve for the speed for the first one, use that speed in the second one, and then solve with the new length, I should be able to solve for the fundamental frequency. All right, so let's take a look at this. So if this is exactly half a wave, so remember a full wave would look something like this. Right away I can just say, well, a wavelength must be 70 times 2, which is 140 centimeters, or 1.40 meters. So right away I'm going to say, well, that's my first one. The wavelength is 1.4 meters. And if the fundamental frequency is 262 hertz, I should be able to solve for the speed. So looking back up here, it says, well, the speed is equal to f lambda. V is equal to f lambda. So if I use that equation, say, well, V is equal to f o lambda o, I should be able to solve for the speed of that. So 262 hertz multiplied by 1.4. 262 times 1.40, I get 366.8 meters per second. I'm going to keep that whole number. It's not my final answer, but that's just the answer I'm going to use at this point. So right away, I know that if I were to change the string to now 50 centimeters, so a new distance of 50 centimeters, well, that means that the wavelength, which must be 2 of these, must be exactly 1 meter. Because 2 times half gives us a full meter in this case. So if I'm going to use that same speed and say, well, the speed that I got here is actually equal to the speed I have down below, 366.8 meters per second. And I know the wavelength to be 1 meters. I should be able to rearrange this equation to solve for the new fundamental frequency. Well, the fundamental frequency would then just be the speed divided by the wavelength that we're referring to. So in other words, 366.8 divided by 1, I should be able to do that in my head. I end up getting 367 hertz. Once again, I'm just rounding to 3 significant digits for this case. And there we go. So step 1 was I solved for the speed. Since the tension was the same, the string was the same material, therefore the speed must be consistent. It doesn't matter if you cut it. The only difference is now traveling over a smaller distance. So therefore, in order to have a fundamental frequency, we must then use that speed and change the wavelength to the 0.5, or in other words, 1 meter as a full wavelength to give us an answer here of 367 hertz. All right, so try the questions that follow for the standing waves. And that's it.